Chapter 5, Thermochemistry. Section 5.1, Energy. Energy is the ability to do work or transfer heat. Energy used to cause an object that has mass to move is called work. Energy used to cause the temperature of an object to rise is called heat. Potential energy is energy an object possesses by virtue of its position or chemical composition. Kinetic energy is energy an object possesses by virtue of its motion. And we have an equation, kinetic energy equals 1/2 times the mass times velocity squared. Units of energy, the metric unit for energy is the joule, which is a capital J, and it is equal to 1 kilogram meters squared per second squared. An older non-metric unit is still in widespread use, and that is the calorie, which is symbolized CAL. 1 calorie is equal to 4.184 joules. System and surroundings. The system includes the molecules we want to study. Here in this picture, the hydrogen and oxygen molecules. And the surroundings are everything else. Here, it's the cylinder and the piston. Work. Energy used to move an object over some distance is work. And we have an equation, force times distance equals work. Energy can also be transferred as heat. Heat flows from warmer objects to cooler objects. And we can also convert energy. We also have to understand the law of conservation of energy, which says that energy, like matter, cannot be created or destroyed, but it can be converted. Energy can be converted from one type to another. For example, the cyclist above has potential energy as she sits on top of the hill. As she coasts down the hill, her potential energy is converted to kinetic energy. And then at the bottom of the hill, all of the potential energy that she did have at the top of the hill is now kinetic energy. Sample exercise 5.1, describing and calculating energy changes. A bowler lifts a 5.4 kilogram or 12-pound bowling ball from the ground level to a height of 1.6 meters or 5.2 feet, and then drops the ball back to the ground. What happens to the potential energy of the bowling ball as it is raised from the ground? What quantity of work in joules is used to raise the ball? After the ball is dropped, it gains kinetic energy. If we assume that all of the work done in part B has been converted to kinetic energy by the time the ball strikes the ground, what's the speed of the ball at the instant just before it hits the ground? Note, the force due to gravity is mass times g, where g is the gravitational constant, and that's equal to 9.8 meters per second squared. We can calculate the work done in lifting the ball by using equation 5.3, which is work equals force times distance. The kinetic energy of the ball at the moment of impact equals its initial potential energy. We can use kinetic energy in equation 5.10 to calculate the speed at impact. Because the bowling ball is raised to a greater height above the ground, its potential energy increases. The ball has a mass of 5.4 kilograms, and it is lifted a distance of 1.6 meters. To calculate the work performed to raise the ball, we use both equation 5.3 and force equals mass times gravitational pull for the force that's due to gravity. So here we have work equals force times distance, and then substituting into the equation, we have mass times gravity for the force, and then times the distance. So we kind of combine the two equations there. Our mass was 5.4 kilograms, the force due to gravity 9.8 meters per second squared, and the distance in meters is 1.6 meters. Be very careful with this calculation that you're using the correct units and that your units are in agreement. If you have the correct units, kilograms, meters squared per second squared, then you can simply abbreviate that with a joule. So in this case, we have 85 joules. The bowler has done 85 joules of work to lift the ball to a height of 1.6 meters. When the ball is dropped, its potential energy is converted to kinetic energy. At the instant just before the ball hits the ground, we assume that the kinetic energy is equal to the work done in part B, 85 kilojoules. Okay, so the kinetic energy equation has been rearranged to solve for velocity. We need to get rid of the fraction 1/2. So dividing by 1/2 is the same thing as multiplying by 2, and so we have 2 times the kinetic energy. And we're also dividing by the mass to get rid of that, or put that on the other side of the equation. And then we can't forget that we need to take the square root. Our kinetic energy was 85 joules, so we're multiplying 2 times 85. And our mass of the bowling ball was 5.4 kilograms. Notice that the kilograms are going to cancel out, and you're going to be left with meters per second for the speed. Work must be done in part B to increase the potential energy of the ball, which is in accord with our experience. The units are appropriate in both parts B and C. The work is in units of joules and the speed in units of meters per second. In part C, we have carried an additional digit in the intermediate calculation involving the square root, but we report the final value to only 2 significant figures as appropriate. A speed of 1 meter per second is roughly 2 miles per hour, so the bowling ball has a speed greater than 10 miles per hour upon impact. For practice, please answer this question. What is the kinetic energy in joules of an argon atom moving with a speed of 650 meters per second, a mole of argon atoms moving with a speed of 650 meters per second, and I want you to think about the fact that 1 atomic mass unit is equal to 1.66 times 10 to the negative 27th kilograms. Please consult your periodic table for the average atomic weight for argon.